Okay. So on the Cauchy-Riemann, or Cauchy-Euler, got Riemann on the brain, Cauchy-Euler equation, it was x squared y plus xy prime plus lambda y equals 0 with y of 1 equal to 0, y prime of e equals 0. And you very obviously got the right general solution for y. You then said that lambda n was 2n plus 1 pi squared divided by 4. Now I haven't solved this equation, I'm not going to. But the nature of the error is pretty obvious. Okay. Where n equals 1, 2, 3, 4. Now, your solution might well have been right, and I think I'm going to go ahead and override and give you credit for it. The solution given by the web assign is extremely close to this. Identical to yours, except I put the 1/4 out in front. That shouldn't make a difference. I don't think WebAssign would distinguish between this and this. I mean, it would distinguish, but it would give credit for either. And then the pi squared out in front, that's not a problem. And it's just that WebAssign uses 2n minus 1 quantity squared instead of 2n plus 1 quantity squared. And this is with n equal 1, 2, 3, and so forth. Okay, so this is the given solution. This is a perfectly valid solution. If you specify n equals 0, 1, 2, and so forth. Okay, because obviously here if n equals 0, you get a 1 here times pi squared over 4. And here if n equals 1, you get a 1 here. And again times pi squared over 4. So for n equals 0 here, you get the same thing you get for n equals 1 here. And for any value of n, 2n minus 1 is going to be the same as what you would get here if n was 1 less. Because if you replace n by n minus 1, well, you get 2n minus 2 plus 1, which is 2n minus 1. Okay, so I'm not going to say any more about that. I'm going to give you credit for that because obviously you did everything right, and WebAssign didn't ask you to specify your values of n. So you fulfilled all the requirements of the question, but generally we're going to let n be 1, 2, 3, and so forth. So you kind of want to keep that in mind. You have your first eigenvalue or your first harmonic. If you're talking about waves on a string, you don't have a 0th harmonic, and you usually won't talk about a 0th eigenvalue, at least not with the current author, and not generally. Okay, so generally we're going to assume n is 1, 2, 3, and you want to be sure you do that. Okay, now the next problem is pretty interesting. We're going to go ahead and work it out. And I'm not sure where you might have gone wrong on this because it's very similar to the other problems. But you've got the equation, and we're using x. Okay, yeah, because this could correspond again to waves on a string. Okay. so here's your equation. And where are we? Okay, you got y of 0 equals 0, and y of L equals 0. Now remember, this is the way we're usually going to write it if you got a string of length L. Okay, so this is your tension, this is your density, and this is omega. Now you remember from physics that your velocity of propagation is the square root of t divided by mass per unit length, which is going to correspond to your density. So that's your context here. And you might want to just review a little physics on waves and strings, standing waves and strings, which is what this is, because your boundary conditions have the string stationary at both ends. Well, with that context, we go ahead and solve it, and just for economy of notation, I'll use y double prime, and then it's plus rho omega over t times y equals 0. And just for a little additional color, note that rho over t is just the reciprocal of t over rho. So this is like the reciprocal of your squared velocity. So I'm just going to kind of write that over here. In parentheses, you got y double prime plus omega over c squared times y equals 0. That's important if you're dealing with a wave equation, and you are dealing with the spatial component of a wave equation when you're doing this problem. Okay, so anyhow, very easy to solve this. We get it looks a little bit like an E, and it was, but I'm going to call it C1 times the cosine of, that omega should be squared. It bothered me here, and it's really bothered me here because we want to get an omega here. Okay, so we get a cosine of rho omega squared over t, and then a C2 times a sine of rho omega squared over t. And that's very straightforward. You solve these problems, so I don't go through the details here. And of course, this could be A times the cosine of rho omega squared over t plus phi. This could also be written as rho omega squared over c squared. Okay, because of this. Now, what we're really after is the eigenvalues. So I'm going to stop making the analogies here, or the correspondences between the wave equation and so forth, and let's just go to what WebAssign is actually asking you to do, or what I'm asking you to do, because I'm letting WebAssign ask you. I'll comment on WebAssign. I'm not happy with WebAssign in some courses, but I'm very happy with WebAssign in this course. Gives you a good, rigorous course. In other courses, and I've only sampled a couple, it lacks what I consider the appropriate rigor. Okay, so you're getting a good course here, in other words. At least as far as WebAssign is concerned. You can make your own judgment about what I'm doing. So here you have it. Now you have your initial conditions. So except for the notation, this is no different than anything else you've done. At least I think it's no different. I haven't worked it out yet. I might be surprised, but I don't think so. And I don't have my x in this solution. Fortunately, I left myself room to put it in there. Okay. Not having an x, I didn't have anything to substitute 0 for, so I caught myself before I got too far along. So this tells you that using this notation, a cosine of phi equals 0, using this form of the solution. And y of L implies that a cosine of cosine of rho omega squared over t times L equals 0. Now at this point it does get a little bit, and I left phi off there. It does get a little bit complicated because unless you assume that phi is 0 or something, but fortunately you can do that. Okay, let's fix this. Okay, this tells you I'm running out of room here, which is unfortunate because I would like to keep this all in one board, and I probably will because I'll probably leave a couple of steps for you to work out. But if the cosine of phi is 0, this means phi has to be a multiple of pi. And I'm just going to skip to phi equals n pi. And you see right here that your eigenvalues are starting to emerge. You have this restriction. Now if phi equals n pi, then you have a cosine of this plus a multiple of pi equals 0. And that means that L times rho omega squared over t also has to be a multiple of pi. Now I'm going to let you work that out. I'll also mention that, well, I'm not going to mention it. I'm going to just stick with this. Turns out n could be any integer, positive or negative. We're not going to worry about that. If you have a negative integer, you just get the same solution a little bit of time later. There's our condition, and that's what you've got to have. And of course now you're looking for your omegas. So I have just room to do this, I think. I know it'll come out on this one. So omega n is going to equal what? And of course we could put an n on this omega, because it's the omega that makes it work. Omega being your angular frequency, which along with your tension determines your speed of propagation. And again, you can think back to the way waves form on a string in order to understand the connection here. And that's critical to understanding what this is really telling you. As far as just solving Webb-Assein's problem, you don't need to understand any of this. But I wanted to make the connection because you do have the physics background. Okay. So that's that one. And looking at the time, I want to have plenty of time to get into Laplace transforms. So I'm going to recommend you go back and look at number 9. If you do and you don't think you have it, we can come back and take a look at it. Okay. Now let's move on to Laplace transforms, which is really, really neat. Unbelievably neat, and I hope you find it that way. Okay, let me